Hi, everyone. I'm sorry not to be able to be there with you in person today, but I'm really excited to be able to give this talk virtually about 21st century conservation and Audubon's transition to zero emissions. You'll hear a lot about this over the course of the day, and I'm really just super, super pleased to talk about this topic. My name is Stephen Porder. I am a professor of ecology, evolutionary, and organismal biology at Brown, where I'm also a member of the Institute for Environment and Society. I also serve as the Provost for Sustainability there, where I oversee Brown's transition to a zero emissions future. And I've been on the Audubon board for a couple of years now. I want to start this talk by thinking about Audubon's mission and how that mission needs to evolve, at least in my opinion, in the 21st century. So I put up our mission statement here. The mission of the Audubon Society of Rhode Island is to protect birds, other wildlife, and their habitats through conservation, education, and advocacy for the benefit of people and all living things. And if you look in our 2020 to 2025 plan, what you'll see is language that looks a lot like the language I would imagine of other conservation organizations, um, focusing on the radical and rapid changes to the environment that humans are precipitating. So the web of habitat, food chains, and species interaction is being altered in ways and at a pace such that the natural processes of evolution and adaptation cannot keep up. It is cliche, but it is an apt description to say that the dramatic loss of birds is the proverbial canary in the coal mine for the impact of the climate crisis on humans. And it's that last sentence, or the last piece of the sentence, that I want to focus on here. The proverbial canary in the coal mine for the impact of the climate crisis. I'm going to argue today, and I think there's overwhelming scientific evidence to support this, that climate change, more than anything else, will impact Audubon's ability to carry out its mission of conservation and the preservation of all species. To give you an example of how climate change is not just something in the future, but in the present, I want to share just one piece of one paper, one scientific paper, and one result from that paper as an example. This was a study where the authors tried to figure out um, whether climate and other factors were already affecting the populations of animals. So they looked at places around the world where there had been population increases or population decreases, shown here on the left-hand side of the graph. They looked at mammals and they looked at birds, and they tried to see whether the rate of warming, shown down here at the bottom, or the rate of land use change, or the body mass of animals, or whether there was a protected area, affected whether or not the population was increasing or decreasing. And this dotted horizontal line you see shows the zero line, meaning that they couldn't see an effect of that particular factor. And the only thing they could see already was that the rate of climate warming was adversely affecting, that is, decreasing the population of both birds and mammals. So climate change is not a future problem. Climate change is a now problem. And so I would argue, and other members of the board have argued, and I think we're at a point now where we realize as a community that as a 21st century conservation organization, the Audubon Society of Rhode Island must grapple with climate change in a very serious way. So today I'm going to talk to you about three things related to how I think and how we think grappling uh, grappling with climate change might play out in the coming years. The first piece is really just to level set and explain a bit about what we know about the climate system and why it is changing, just to make sure we're all on the same page. I'm going to then very briefly talk about how much climate is changing to give you a sense of context for how urgent the situation is. This will not be news to many of you. And finally, I'm going to talk a little bit and about what I think and what others think ASRI should do about this problem. Obviously, there's our ability to solve it by ourselves is negligible, but our ability to act as leaders is actually quite substantial, and that's what I want to talk about at the end. So let's just jump right in and talk about why is the climate changing. You've probably learned a lot about this through the media or through your own work or conversations, but it might surprise you to know that our understanding of the drivers of climate go back almost now 2 centuries. And they go back to a woman named Eunice Foote, who in the 1850s did a series of really beautiful experiments where she put carbon dioxide in tubes and looked at the effect of sunlight on the temperature in those tubes and then compared those to the temperature of tubes filled with other gases. And what she concluded was that not only was that the concentration of carbon dioxide in the atmosphere controlled the temperature, but also she hypothesized that if carbon dioxide levels had been higher in the past, the Earth must have been warmer than it was in 1850. This was pioneering work uh, for which she has only recently been credited, in large part because as a woman, she was not allowed to present at the scientific conferences. And so another scientist, with her permission, presented her work because it was not considered appropriate for her to be involved in that sort of conversation. Nonetheless, incredibly pioneering work, and it's wonderful that she's finally getting the recognition that she deserves. If you fast forward from her papers in the 1850s to the late 1800s, we now go to the Swedish chemist Svante Arrhenius. Now, Arrhenius is a very famous chemist for a number of reasons, but in 1896, he published a paper called On the Influence of Carbonic Acid in the Air upon the Temperature on the Ground. Carbonic acid is what we called CO2 in those days. And this paper represents the very first climate model. And what I mean by model is that Arrhenius essentially calculated for different levels of CO2 in the air what the temperature of the Earth should be. And I love this table on the right-hand side because it's incredible the detail that he was able to achieve even in 1896. So on the top bar, what you'll see are different concentrations of carbon dioxide in the air relative to the atmosphere at the time. So the left-hand column, 2/3 of the amount of carbon dioxide at the time. The next one over to the right, 1.5 times, 2 times, 2.5 times, and 3 times. He was actually able to do this calculation for different latitudes, going from the northernmost land to the southernmost, and for different times of the year, so December through February, May, March through May, etc. And each of these numbers that you see in the main table is how much the temperature would change given a change in carbon dioxide in the atmosphere, according to his climate model. Again, the very first climate model in the world. What's remarkable about this, among many things, is that if you use his climate model and you say, okay, what were the actual carbon dioxide concentrations in the atmosphere in 1960, 1970, 1980, 1990, et cetera? If you run that model against how much the temperature actually changed, his model output is in the black dots, that line going up to the right. The actual temperature change is in the open circles. His model from 1896 does an incredibly good job of predicting what happened in the second half of the 20th century. And what's remarkable about that, right, is that it's a one factor model. Only carbon dioxide is in this model. And yet it does an incredibly good job of predicting what actually happened, making us very confident that the model was fairly close to right. The deviation, as an aside, the deviation that you see, that is where the open circles don't fall on the line, is largely a result of a cycle called El Nino and La Nina, which is a 5 to 7 year climate fluctuation that Arrhenius knew nothing about, but that we've learned quite a bunch about since. Okay, so from Arrhenius's predictions in the late 1890s, we now move to the 1930s. And work by a gentleman named Guy Callender uh, uh, who actually gathered from 140 places around the world temperature data from the 1880s to the 1930s. So this figure from his paper in 1938 is titled Temperature Variations of the Zones of the Earth, 10-year departures from the mean, so departures from the average temperature. And what he put in this paper is really remarkable. In 1938, he already had calculated that this black line, which was showing the rising temperatures calculated from the average of these stations, he already had calculated that some of that was a result of CO2 coming out of coal-fired power plants and the beginning of the use of oil, but really here mostly coal. So by 1938, we already had a sense not only of how much CO2 uh, affected the atmosphere, but also that it was already affecting the atmosphere and the temperature on the ground. So from that brief lesson in climate history, let's move forward to the 1990s. Here's where international scientific effort really begins in earnest. We have the Earth Summit in Rio in 1992, and in preparation for that, the first report from the Interpanel Governmental on Climate Change. There have since been not one, two, three, four, five. We just had the sixth Intergovernmental Panel report. The important thing to know about this is that it is actually an international consensus. The summary for policymakers, every single word has to be agreed upon by the 100, almost 200 countries that are represented at the climate meetings. And so they're a very, very conservative estimate of what's going on. They don't include fringe ideas. They don't include anything that is controversial, really. So let me then sum up for you from Eunice Foote to the present what we understand about climate. Here it is in a nutshell. The more carbon dioxide we emit to the atmosphere from burning fossil fuels and burning forests, the more the temperature will rise. Not only that, but it's a linear relationship. This is actually quite surprising. It turns out to be the case that the total amount of CO2, not the amount we emit each year, but the total amount emitted since we started emitting, will linearly translate into a temperature rise. And if you don't like the cartoon version of that, here's the IPCC's most recent version of that. Same axes, total amount of CO2 emitted on the x-axis, temperature rise in degrees Celsius on the y-axis relative to an average. The black line shows you historically what we have emitted over time, the total amount from 1850 forward. The colored bands show how much we have left to stay within a certain temperature limit. So the blue box basically shows you how much more carbon we can emit before we exceed the 1.5 degree Celsius threshold that many people think is sort of the last reasonable and prudent threshold before things get really, really unpleasant. And you can see we have very little time. In fact, this number is now closer to, we have closer to a few hundred gigatons of carbon left, having emitted close to 2,800 in total. We also know from more modern climate work that there is an opportunity to solve this problem. Warming will stop almost immediately when we stop emitting CO2 to the atmosphere. Unfortunately, sea level rise will continue for decades, and that's because the ocean is still responding to the things we've already done. The ocean is very slow to respond. It has a huge amount of thermal mass. It's slow to change temperature, and it's slow to react to changes in the atmosphere. And as a result, sea level rise will continue for quite some time as water warms and the ocean expands and ice melts off land. But warming itself, the warming of the air, will stop within probably a decade. And by the second half of this century, there is a real chance, if we act rapidly, if we seize the moment, that we could reverse climate change and actually begin to cool ourselves back down, which is a really exciting possibility that I wouldn't have thought was on the horizon if you had asked me, say, a decade ago. There's one more thing I want to make very, very clear before I move on to the next section, and that is where all these CO2 emissions are coming from. Yes, it's multifaceted, but at the end of the day, three-quarters of the problem is CO2 released as a result of our need for energy, our energy to make things in industry, our energy to transport ourselves around, our energy to heat and cool our buildings. This is the source of CO2 that we have to address most urgently. And fortunately for us, it is the source of CO2 that for which solutions are emerging at an incredible pace. So that's where I want to move at the end of the talk. But before I do that, I want to move from to give you a little bit of context to move from why the climate is changing to how much is the climate changing. And I want to give you some context in the short term and then also a little bit in the long term. So probably the most famous data set for the change in CO2 in the atmosphere over time comes from the Mauna Loa Observatory high up in the mountains of Hawaii, on the big island of Hawaii. And this is called the Keeling curve, named after Professor Keeling, who was the first to observe it. And the Mauna Loa Observatory has been taking CO2 measurements in the air for decades, these data going back to the 1960s. And what you can see is the concentration is rising over time. That shouldn't surprise anyone, given what I've been saying so far. Interestingly, the sawtooth pattern, to give you a sense of scale, the sawtooth pattern is the breathing in and out of plants. So in the northern hemisphere, there is much more land and therefore many more plants. And so in the northern summer, when plants are photosynthesizing, their leaves are out, you actually draw down CO2 in the atmosphere. That results for the little downward in the sawtooth. And it's not balanced by plants in the southern hemisphere simply because there isn't as much land in the southern hemisphere. And in the northern winter, or in the northern fall, winter, spring, when plants drop their leaves and those leaves decompose, you see a rise up in the sawtooth of CO2 in the atmosphere, and then a drawback down in the northern spring and summer. That's the sawtooth pattern. But compare it in magnitude to the rise that we're observing. The entire biosphere of the planet, breathing in and breathing out, is a teeny little sawtooth on the imprint of rising CO2 as a result of fossil fuel combustion. And to give us a longer term context beyond a few decades, here's a graph that goes back not years, not decades, but thousands of years. So these are data from bubbles trapped in ice in Antarctica. We can drill down into that ice and go back 800,000 years in time and look at the changes of CO2 in the concentration of the CO2 in those air bubbles in different layers of the ice. And this sawtooth pattern that you're seeing here is actually the difference between glacial periods, where CO2 is quite low, down by about 180 parts per million, and so-called interglacial periods, warmer periods like we're in now. And so as you move from the deep past, 800,000 years ago, to the right-hand side to zero, you can see that until about 10,000 years ago, we were in a glacial period, and human civilization has really benefited from the relatively stable and warm climate that has been caused by higher CO2 more recently. So this is 800,000 years of changes in CO2 until the present, where we are now up here. So when we talk about evolution and organisms, including humans, having difficulty adjusting to rapid change, this is what rapid change looks like. 800,000 years of glacial, interglacial cycles, and 100 years of incredibly rapid CO2 rise in the atmosphere, and therefore incredibly rapid warming. To give you another sense of that, I'm going to show this map, which many of you have seen before because I give this talk a lot. What this is showing, obviously, is a map of the world, but this map is color-coded by temperature. So, for example, in the middle of the map, in West Africa, this orange blob indicates that during the time period 1880 to 1884, Western Africa was about 1 degree Celsius warmer than Western Africa was in the middle of the 20th century compared to the middle of the 20th century average. In contrast, Rhode Island in 1880 to 1884 was a little bit colder, maybe 1 degree Celsius colder than it was during the middle of the 20th century. So each place on this map is color coded according to whether it was warmer or colder than that same place was in the middle of the 20th century. So with that introduction, I'm going to play it forward in time from the 1880s, shown here, through the 1890s into the 1900s. And I want you to look for when a change occurs. Here we are in the 1920s, 30s, 40s, 60s, 80s, 90s, 2000s, 2010s. 2023 was by far the warmest year on record. What this map is showing you is 5-year running averages. Nonetheless, warming is unequivocal. And because of the work of pioneers like Eunice Foote, Svante Arrhenius, Guy Callender, and then all of the wonderful climate scientists who have worked for decades since then, including climate scientists at oil companies, climate scientists at government institutions, climate scientists at universities, we now know that this warming is unequivocally tied to our burning of fossil fuels. What I showed you in that previous map is the changes in the average temperature, but I think it's really important to note two other things about climate change. The first is that it's really not the average temperature that affects humans or other organisms. It's the extremes. And when you change the average of the climate, you really change the extremes. This is a graph from the New York Times where they took all of the temperature data from the Northern Hemisphere. And in this case, I'm showing you the temperature data from 1950 to 1980. And they said, okay, sometimes in the Northern Hemisphere, it's cold. So on the y-axis, you have how often something is occurring. And on the x-axis, you have whether it was sort of average, hot, or cold. So in the 1950s to 1980s, they say, okay, sometimes it's cold. It's very, very rarely extremely cold. Sometimes it's hot. It's very, very rarely extremely hot. These are the data from the 1950s to 1980s. But if you run that forward in time and look at what has happened since then, you see a very different story. Yes, the average for the peak will have changed. That's the map I was showing you before. But look at the extremes on the far right in the 80s, in the 90s, in the 2000s, and in the 2010s. Shifting the average temperature, that is the most frequent temperature, by a degree or two, has huge effects on how many extremely hot days we have and diminishes the number of extremely cold days we have. And as a result, organisms have to deal not just with the difference between, say, an 80-degree day Fahrenheit in the summer versus an 81 degree, but they have to deal with the fact that instead of having one day over 100 every decade, they have 5 days over 100 every year, right? And for things like heat-related mortality, both for humans and others, right, it's the extremes that really matter. The last thing I want to say before I move on to what we can do about it is about sea level rise. Rhode Island, being the ocean state, is going to be profoundly affected by sea level rise. And sea level rise, unfortunately, instead of rising linearly with emissions, the way that air temperature does, it accelerates exponentially. So if you look at sea level rise between the beginning of the 20th century and the present, we've had about 0.2 meters, so about a little less than a foot of, a little less than a foot of sea level rise. But if you look at the rate from 1901 to 1971 was about 1.3 millimeters per year. Then it went up to 1.9, then it's up to 3.7, And by the middle of this century, we expect it to be rising about half a centimeter a year, which is going to force retreat from our coasts all all across Rhode Island. There's no doubt about this, and we need to be planning for it now. Some towns in Rhode Island are doing a great job of that planning, others a little bit less so. Okay, so I've painted a pretty bleak picture so far, but I really want to pivot here because there is a huge opportunity to fix this problem. I wouldn't have said that 15 years ago. I truly believe it now. And so the question we need to be asking ourselves as an organization is and as citizens of the world, is what should we do about it? And so I'm going to focus a little bit now on what ASRI, Audubon Society, should do about it. And I want to return to our mission. The mission of the Audubon Society is to protect birds and other wildlife and their habitats through conservation, education, and advocacy. Okay, so what does this mission mean in a warming world where the world is warming because we are burning fossil fuels? I would put to you today that it means two fundamental things. The first thing it means we need to work to help humans and other animals survive climate change. And I would argue that we do this very well. We're one of the biggest land holders in the state. We protect that land, preserve it. That land provides habitat, it provides cooling to the region. It's well documented that trees help have been cooling the east coast of the United States, actually, and mitigating some of the worst effects of climate change, even so far, and will continue to do so. So this has been the core of our mission, and I think we do it extremely well, and we should be extremely proud of it. But across our facilities, across our meetings, across our footprint, we, like everyone else, rely on fossil fuels to heat and power our facilities, and that contributes to climate change. And here, I think we have an opportunity to lead in a new and exciting way. So in order to explain to you what I mean, I want to talk about the way we currently do business. Somewhere out there in the world, someone is burning natural gas, which is really just fossil gas, uh, in a power plant, which is connected to us, and that is powering the nature center and all of our other buildings. It's powering the pumps to circulate water. It's powering our heating. It's powering our cooling. It's powering our computers. It's powering this projector on which you're viewing this talk. We also own vehicles, and our staff and and the community commutes to our site mostly by car, and that's also burning fossil gas. We cannot continue to rely on fossil fuels to power our lives, and Audubon has an opportunity to take a leadership role in stimulating this transition, in undertaking this transition ourselves, and teaching others how to do it as well. So the proposal on the table today, the plan of action on the table today, is to change our ways rapidly. And what does that mean? By 2030, it means replacing the furnaces in all of the buildings that Audubon operates here in Rhode Island, to replace those with electric heat pumps that will heat and cool our buildings much more efficiently than furnaces do, and importantly, will run only on electricity. And at the same time, we will replace our vehicles and our grounds equipment to also be fully electric. This alone will reduce our emissions by somewhere around 30%. And the reason it won't reduce our emissions to zero, of course, is over here on the left-hand side, because someone is still burning fossil fuels to provide all of our electricity. The emissions reductions come from the fact that heat pumps and electric vehicles and electric ground equipment are simply way more efficient than burning stuff on site. The next step, again by 2030, will be to change our source of electricity and rely on 100% renewable electricity by installing solar panels on Audubon land. I think it's important that Audubon put its land where its mouth is, so to speak, and produce some of its own or all of its own power. We have enough land for both habitat and some solar panels. This will drop our emissions to net zero. And it's only net zero because, of course, solar panels don't produce at night. They produce less in the winter. But on an annual basis, these panels will produce as much electricity as Audubon facilities uh, 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 consume. That's the 2030 plan, but we can't stop there. Net zero is not true zero because we're still relying on a fossil fuel powered grid for the times when the sun isn't shining. So our our plan by 20, oh, sorry. Let me just say though that this itself is an important step. And what will you as the public or Audubon members see that's different? You won't really see the heat pumps. You may see the electric vehicles. You certainly will hear how much less noise they produce. But what you may see is solar car parts, a solar carport, and EV charging at the Bristol Center, for example. And hopefully, many more of the cars in our parking lot will be electric. In addition, you may see some of the land at the Audubon Center used for pollinator-friendly solar. There's an enormous amount of work being done to understand how to best site solar panels in a way that is pollinator and habitat friendly. And it is important, at least in my view, that Audubon model this behavior for other solar developers, both in the state and in the region. Yes, carports are important. Yes, roofs are important. We're also going to need to use some land for solar, and Audubon can lead in responsibly showing where that land can be and how that land can serve more than one purpose. By 2040, though, we have a plan to get not just to net zero, but to true zero. How is that? Well, by then, the Rhode Island grid will hopefully, and Audubon will work hard to make this the case, hopefully be a mix of offshore wind, on-site solar, and adding in battery storage to that grid, both in Audubon facilities and also more broadly, will allow us to run 24/7 on renewable electricity. This will require a robust electrical grid, and Audubon will use its advocacy to help push for that. That's an incredibly important reform across the country. We need to strengthen our grids, deliver all of this reliable, inexpensive, renewable power to homes and businesses and industry. But in combination, offshore wind, on-site solar, and batteries will allow ASRI to completely eliminate emissions by 2040. That's what we're calling true zero. So to return and conclude, the mission of we are doing a great job on part of our mission, habitat conservation. We now have a plan to address the elephant in the room, so to speak. How are we going to lead on climate mitigation and education? So what does conservation leadership look like in a warming world? Because world warming because we are using fossil fuels? The future of conservation at ASRI must include both habitat preservation and leadership on emissions reductions. We have a plan for that, and we hope that you will join us in this effort. Thank you very much for your attention, and thank you again for the opportunity to speak. Have a great day.